project 3 is due tomorrow. Is it due at noon tomorrow? Is that right? So some of you asked for extension. Unfortunately, I'm not going to do extension. Right? I gave 4 weeks. That's plenty of time. And there's no homeworks during this period. There's 1 midterm, but there's also a 4 break. Right? So if you cannot finish, you cannot finish. Right? That's nothing much I can do. I do give you this option of 3 days after deadline. You can still submit, but every day is subject to 10% penalty, which means you can submit. If you submit by noon on Saturday, you get 10% off automatically. You submit by noon on Sunday, you get 20% off. You submit by noon on Monday, you get 30% off. But after that, with 0, right? Even if you submit a code that's completely working, you get 0 credit. Okay. So that's regarding project 3, and I will release project 4 on Tuesday, next lecture. Project 4 will be on external merge sort, the thing we are discussing right now. Then there will be 1 more project after that. Then we're done. There will be 2 more homeworks before the final exam. So hopefully I can release the 4th homework in a week or 2. Okay, depending on how fast we can solve things. With that said, let's continue on the discussion of merge sort. So we talked about merge sort last lecture, and we finished pretty much all the discussion except one thing, which is if you think about phase 1, in phase 1, what do? You load the pages into the memory of size B, of course. You load them in. You load every view of them in, and you sort. And you dump to disk. And that's what we're doing. And what this gives you is a run of B pages that's sorted. This is a single run of B pages that's sorted. And you do so for roughly over B runs, and each run is sorted.
Could you remind me again here, in this first phase, if we're loading B pages in, then how can we, so we have to sort internally in each page. And
we have to sort not internally each page, we sort all these pages together. You view this as the input data of B pages, you sort them all together.
Right.
So that gives you a run of B sorted pages.
Oh, I see.
B sorted pages doesn't mean each page is sorted, but all of them are sorted.
I see, because we can do an in-memory.
We can do an in-place, in-memory sort.
Yeah, okay.
You're not sorting each page individually, rather here you sort these B pages together.
Right.
Okay. So that's the picture. However, this has a problem, right? If you think about it, one way when you go for interview or when you go on and do your work, one way to test your algorithm, to check whether it's a good design or not, is to check the extreme case. Extreme case, right? What would be an extreme case here? Well, one extreme case is that these pages are sorted to begin with. You understand what I'm saying? However, of course, you don't know that. God knows this, right? You're not God. So you don't know these are actually sorted. To verify that it is actually sorted, how do you verify something is already sorted?
You have to run through and check.
You have to run through and check, right? You have to run through and check. To check something is sorted or not, it takes linear time, right? You just remember the last value you read and compare against the next value. If every 2 value is in order, by the end of the day you're done, right? But it takes linear time. However, if you run our algorithm as we discussed last lecture, unless you do this linear checking first, suppose we don't do that, we just proceed with the algorithm that's given. Even if all the pages are sorted already, you still will pay pay this many IOs to sort them. You follow me? Even if they are sorted. And this obviously is not ideal, right? Ideally, we want to have an algorithm that if they are not sorted, yes, I will pay this many IOs, but if they are sorted, hopefully I will pay just 10 IOs. Right? Somehow I can do this automatically. And that's motivation number one. Motivation number two is if we can somehow reduce the number of rounds in the first phase, in other words, if we can increase the size of each round, we can reduce the total number of phases we need. If we can increase this, for example, from B to 2B, size of each round, then we can reduce the number of rounds and reduce the total number of phases needed. For those two reasons, we need a better algorithm in the first phase. Instead of loading B pages and sort them, we need a better algorithm. That's essentially this algorithm right here. It's called two-element sort. Why it's called tournament sort is because the way it runs is kind of like running a tournament. It's like if you have a soccer tournament or football tournament, you put two teams against each other. The winner goes to the next phase. The losers go to another port. Right? You have playoffs. You have all the, 4 teams go to playoffs. The other teams check whether the ball eligible or not. Right? So things like that. That's what we call a tournament, and that's precisely how this algorithm works. Okay. So let me show you how this algorithm works. I partition my memory into two heap structures. Two heap structures. And they are H1 and H2 respectively. Note that the heap structure here is different from the heap file we talked about. Heap structure here is the data structure concept. Essentially, you can view them as a binary tree, meaning elements in a heap are sorted. Okay, elements in a heap are sorted. Okay. Partition them into H1 and H2. So it looks like this. Right, H1 here. And H2 here. Initially, both of them are empty. Both of them are empty. Okay. What I will do is I will have one input buffer and one output buffer. Okay? So this is my memory. Okay? And here is your disk again. What you're going to do is you load a page at a time. That's simple, right? You load this in. And what you're going to do is you look at each of these elements and you insert into one of the heaps. You push them into one of the heaps. It depends on the matter. The tricky part is which heap you push a particular element into. Okay. What you do is you push this. You load this page of data in. Initially, you push them into your H2 heap. Let me make sure I'm consistent with the slides here. H1 to H1. So you load them into. I think you load them into H1. Yes. You load them into H1 heap. By loading them into H1 heap, what happens? They are sorted. Right? So this becomes empty. And this element become sorted. Become sorted. Do you follow me? Initially, they were not sorted in the page you load them in, but now once you push them into H1 heap, they become sorted. Now clear? Now what I gonna do? I will remove the element, the element from H1. So write it down. So the page. Okay. Then I will load another page at this point. So the second page comes in. Okay? Is that clear? And what I'm gonna do is I start pushing the smallest element from H1 to the output. In another word, H1.hat. You remove the hat of H1 and push it to the output. The hat is the smallest. Okay, so this is a single element that goes here. Now clear? Do you follow me? Do you guys follow me? Okay. Now suppose you store this element here in the input buffer. Then you compare the smallest element here versus the last element you push to the output. You follow me? Yes or no?
Well, it says in the slide, like, do you do the comparison before you actually push it to the output?
Well, if you look at this, the slides, what happened is it will keep removing element from the H1, the head of H1. If it's empty, you will reset that to H2, which I will explain in a minute what H2 does. If there's records left, if there's no record left, you will read a page from, you will read a new record, but in order to optimize the I/O, instead of reading one record at a time, I read a page at a time.
Right.
But effectively, you can think about you're checking one record at a time. So do people follow Charlie's question? Because in the slide, it says you read a new record at a time. But if you do that, you're paying one I/O per record. So instead of doing that, I will optimize that a little bit. I will read in a page at a time and hold it in the input buffer. But effectively, that's the same as read one record at a time because I pay one I/O for this many records, then I just push one record out from that page.
Oh, and I skipped over the part where it says put M in the output buffer. I didn't read that part.
Yes,
Okay.
yes. Put M in the output.
Okay.
That's what I'm doing. Okay? So, in that case, let's follow the slides strictly, right? If you wanna, you're gonna make sure you can understand this with reference to slide. So this is M, the smallest one you push to the output. Is that clear? So you keep pushing, let's say we keep pushing from the H1. So all of this will come here. Is that clear? Whenever this is filled, I will dump to the output, to the disk. And this becomes empty. At some point, you run out of elements from H1. H1 becomes empty. You follow me? Obviously, that will happen eventually. At this point, you check the next record from your input page. Is that clear? From the input buffer. You know, if we follow the slide strictly, you don't even need to sort them. You just check one record at a time according to the order they originally have in the page, which may not be sorted. That's okay. We check the first record here. Let's say that record is R. And the last record I push to the output, let's say that's N. Is that clear? Yes or no? Do you follow me? Now, there are only two possible cases, right? There are only two possible cases. One is, the other is, right? There are only two possible cases. If R is greater or equal than M, what do you do? In case 2, R goes to H1. What about case 1? Well, if case 1, R comes to H2. That's it. That's the argument. Why this works? Why this works? Well, if you think about it, it's very intuitive, right? Sorry.
Well, yeah, I'm just going to say why it works. So
Yeah, go ahead.
So if R is greater than or equal to M, you know that you've popped things out of H1
Yes.
and put them in the output in sorted order. And so if R is greater than or equal to M, you can put it into H1 and eventually it'll be popped out, such
From
that
H1.
it's, from H1 such that it's bigger than things you've already put in the output.
That's the keyword. If R is greater than and equal to M, and you push to H1, eventually R will be pop out from H1 and push to the output buffer. The important guarantee here is that R will be larger than or equal to all the elements you have pushed out from H1 and insert into the output buffer so far. You follow me?
But if it's smaller, you can't safely.
Exactly. But if it's smaller, you can't push to H1 and still ensure that all the elements pushed out from H1 so far observe the orders you want to enforce. That's the critical observation. Do you follow me? And that's why if R is smaller than M, you push to H2. And this process continues until when? Until H1 become empty, meaning that there are no more elements for you to push to output from H1, and there are no more ammunition to H1 at all. So it's kind of like you run out of your bullets from H1. And you ask for supply, but there are no more supply. Why there are no more supply? Because the next record happened to be smaller than the last element you push out from H1. So you run out of bullets in H1 and there are no more supply. That's when you have to do what? You call it a round. At that point, H2 might look like this. Why this basically are all the elements that were not able to go to H1 have been pushed to H2 so far. At this point, what do? Well, you move all of this to, they become H1 up. They become H1, and that's why they keep having erasers. I think people just keep dropping them. I see like at least 4 of them. Okay, so you copy your H2 to H1, and you start a new round. The new round proceeds in the exact same fashion as what we have done so far. So if you're not clear, just let me explain a little bit further. By copying this guy from H2 to H1, H2 become empty again, and you can start pushing H1 to the output. The elements from H1 to the output. However, keep in mind, this is a new run, meaning that whatever you have pushed to the output in the last round, they become a round. And you now, in this new round, it start a new round. Why is that? The reason is the element here will be smaller than the last value you push to H1. So they cannot be in the same run, still ensuring the sorted order. So they have to be in a new run. So every new run gives you a new run. And then, from here, things just proceed as normal, right? So you start pushing them to the output, this run grows, and some will go to H2. At some point, this will become empty, and the next record will be again smaller than the last element you push to the output. That signifies yet another run. By that time, you produce yet another run. You start producing the next run, so on and so forth. So that's this algorithm. This is what we call tournament sort. Why it's called tournament? Because you compare the next record against the last record push to the output. Winner go to H1, loser go to H2. It's kind of like a tournament. Do you follow me? And why this algorithm is good? Let's check. Let's now use this algorithm and check this extreme case I have just argued, which is all the input pages are actually sorted. Let's check what happens in this case. What happened in this case? Well, very nicely, every single one of them will go to H1 in order. And you never push even a single element into H2. You follow me? And you produce a single run of n pages. And you are done sorting. And it's linear cost. What is the worst case? Can someone tell me the worst case for this algorithm? Sveta? Yes. Is there reversely sorted? Fantastic. Tell me what happened in that case, would you?
Everything will go into H2 and then
Everything will go to H2. Is that the case?
I think that first they go to H1.
What's your name, by the way?
Shaobo.
Shaobo. Okay, louder. Okay, go.
First they go to H1.
So let's do it, right? So we load the first page. They're here.
Then they go to H1.
The first element, you push them to the first page. You push them to H1. They're sorted, right? And you start pushing them to the output. So you produce a run of one page. What about the next record? The next record will be greater than, greater than, you're loading this page, yes. If I start loading from here, then I'm like almighty, I know you're reversely sorted. So here, you load this, so the next record from here will be what? Less than the last record you push to the output. In fact, all this record will be less than the last record you push to the output. Then what happens? They will go to H2. So you produce a run of only one page. You follow me? However, we can fix this somehow. We can initialize by what? By reading. Initially, what I'm going to do is I'm going to allocate all the available pages to. I'm going to make H1 arbitrarily large and H2 as small as possible. And in my initialization phase, I load as many pages as possible into what? Into H1. That's just my initialization phase. The rest of the algorithm stays the same. You load the page to the input buffer and you proceed, right? But in the initialization phase, I can load as many pages as possible into H1. In the worst case, how many? In the best case, how many pages I can load into H2? Into H1. I can load b minus 2 pages into H1. Why? Because I do have to reserve one page for the output buffer. I do have to reserve one page for the input buffer. My H2 is empty doesn't occupy any space whatsoever. It's just a conceptual construction at this moment. I load B minus 2 pages into H1, so total I have B pages. Why this helps? Because now everything in H1 are sorted. Even though this B minus 2 pages are reversely sorted on disk, but once I load them into into memory, they are properly sorted in H1. Do you follow me? And then I start pushing elements from H1 to the output. The effect of that is what? H1 will shrink over time. It shrinks so much until there's no one left in H1, and by that time my output disk will have exactly B minus 2 pages that are sorted. At this point, what do? Follow the algorithm. What you do is you load the next page. This is B minus 1's page. And check the next record against the last record you push to disk. You know what? This record guaranteed to be smaller than the last record you push to disk. Why? Because this thing is reversely sorted. Do you follow me? And you can do this for every single round. You can do this initialization step at every single round. Meaning that at the beginning of a round, instead of loading just a single page, you load B minus 2 pages. Do you follow me? Yes or no?
So how does that become different then from the first sort we did before?
In this case, you produce no, there's no difference, precisely. However, the difference is the algorithm is agnostic to how the data are sorted on disk. Whether you are properly sorted or inversely sorted, I run the same algorithm. But the nice thing is, by doing this, I can automatically figure out the best case. What should I do? I mean, if they're properly sorted, running this algorithm will give you a single round of n pages. If you were to use the baseline algorithm, the XML merge sort, you always load just B pages and sort them. Then in that case, in the extreme case, when everything is properly sorted, you still need to run through the subsequent phases and do all the merging effort. But using this algorithm, you don't. If they're properly sorted, you produce a single round of n pages, you're done.
So the difference would be in the next phase, you could, I mean, with this algorithm, you could just skip the next phase. If
There will be no next phase,
right,
if they're properly sorted.
But then you'd also have to have some kind of check in the first phase to detect. Like you'd have to say, oh, my first chunk is all the way sorted, and then the largest value from my first phase is smaller than...
No, that's the thing. You don't have to do that check. I mean, it's embedded into the algorithm. Once you do this optimization for your initialization, you need at the beginning of each round, you load B minus 2 pages. At the beginning of each round, you load B minus 2 pages. If you do that with this algorithm, there's no additional checking needed. The algorithm just proceeds naturally and will behave properly according to how data is sorted in your disk.
Well, how would you detect that you're done? That you don't...
Well, you're done by reading when you have read all the pages from disk.
So there's only one phase for this algorithm? There's multiple phases for this algorithm.
What do you mean multiple tables in this?
Phases.
Well, the number of phases, there are two things: number of rounds and number of phases. Right? The number of rounds is how many times you do this H1, H2 swapping business. And number of phases is depending on how many rounds you have. If you have a single round, you can terminate. You only have a single phase, you're done.
Oh, I see.
You check the number of rounds on disk. If you have a single round, you know you can stop. Okay, do others follow? So let me repeat one more time. Okay. Initially, both of your H1 and H2 are empty. That's the beginning of a new round. At the beginning of a new round, you load B minus 2 pages into H1. They are sorted. By the time you load them into H1, they are already sorted because H1 is a heap. Then you start pushing elements from H1 to the output. You push until H1 becomes empty. So initially there will be -2, then shrink. So that's the flow. You push the output buffer then to the disk. It shrinks so much until this becomes empty. Then you load the next page in, check this value against this. If it's bigger than the last value you push, you continue the flow, otherwise it comes here. If it's smaller than that, it comes to here as H1 is empty, that signifies the end of the current run and you start a new run. And when you start a new run, what do? You load B minus 2 pages again. Okay, that's the algorithm. And if you run this algorithm with the argument I just gave you, if the data are already sorted on disk, this will give you a single run of n pages. Why? Because this next record is always going to be larger than the last record you push out from H1. So everything you load from this will just continue this flow nicely. At the end of the day, you have a single run of n pages. Back to Charlie's question, how many phases you have? Well, if you have a single run, you have a single phase. You don't have to run any further phases. However, if you do not have a single phase, single run, you end up with multiple runs. What do? Well, you proceed as the normal XNOR merge sort. You proceed into the merging phase. How many runs does this algorithm produce? Well, obviously that's a variable, depending on the distribution here. The analysis of that actually is quite involved. But as we can tell, the best case is what? One run, n pages. What's the worst case? Well, B minus 2 pages in each run. Why that's the worst case? Because at every run, I load B minus 2 pages and push them to this, sort them, push them to this, and immediately the next record can no longer be pushed to the output. It has to go to H2. That's the worst case. Not even a single record more than B minus 2 pages. So you will have B minus 2 pages. How many runs you will have here? This many runs. Well, this is actually good news. Why? Because in the worst case, the number of runs is roughly similar as our baseline algorithm, which is load B pages, sort them. In other words, if you use this algorithm, you cannot be, you are not losing out. It's kind of I tell you, okay, you go and you bet. In this case, you may win $100, but you may lose $100. But in this case, you may win $1 million. You may lose $102 in the worst case. Obviously, no brainer. Everybody will go with this algorithm. But if you tell somebody, okay, I have this fantastic algorithm. In this case, you win $100. You may lose $100. In this case, you may win $1 million with very small chance, but you may end up losing $1 million too. Most likely, people are not going to use this. People will still use this. The argument, what I was trying to argue is, the worst case of this algorithm is almost as good as your baseline algorithm. So no brainer, but the best case is way better. So no brainer, you always use this. What is the average case? Well, the average case analysis is much involved. I'm not going to go to the details, but I can tell you the results. On average, you have a run of 2 B pages, and the number of run is roughly this many. Okay? Roughly. And the analysis of this is not trivial. You have to assume, you have to consider different kind of distributions of data sorted, and sum up all the possible distributions and derive this number here.
So what's the worst case number of runs again?
You load B minus 2 pages, you sort them at the beginning of each run, but immediately after that, the next record from the next page is already smaller than the last record you push out from each one. So you cannot push any more record to each one, not start a new round. So you load another B minus 2, so on and so forth.
So why is that result in n number of v minus 2 pages?
Well, because each run has v minus 2 pages, you have n pages in total. How many? You tell me how many runs you want to have. It's n divided by this.
Oh, okay.
Okay, with that, we finished the discussion on sorting. Let's move on to the next lecture. All right. We finally are ready to tackle one more component in the kernel, which is query evaluation. Okay. So if you think about what we have done so far in this class, right? We talk about relational algebra, we talk about SQL, we talk about a disk, we talk about files, then we talk about indexing, tree and hash, then we talk about sorting. All these are, it's kind of like starting from the top layer. If you are the user of the database system, we start from the top layer where you write some SQL queries, and we now know this SQL queries will be compiled into relational algebra representation. And then the kernel will start evaluating your query against the underlying files, which are new tables, using those relational algebra representation, and with the help of indexing if there's any, right? That's pretty much what we know so far. But the challenge is, and the question remains, is how exactly the kernel evaluate a particular operator against the underlying file and indexing structures. And that's the discussion we're going to do today. Okay. First of all, we talk about unary operators. What that means is it involves a single table. In other words, we're not discussing drawers. We're discussing selection, projection, things like that first. Then we proceed to joins. Okay. So if you think about, these are the. So we talk about we have fully understood dspace manager, buffer manager, file and access method, relation operators. Now we are looking at this query optimization and execution layer. So what are the possible forms of single table queries you're going to have? Well, these are the possible forms. Pretty much cover all the possible cases, right? For a single table evaluation, right? Single table evaluation. You have a select clause, possibly with distinct. Remember, distinct means that you need to remove duplicates. And you have from clause, but here we talk about single table, so there's only a single table in the from clause. You have the where clause, group by, having, and order by. Okay? The simplest version is what is shown here. Right? Ignore the gray area, gray colored words. Look at only the black colored words. And these represent the simplest form of a single table query you can have, right? Which is select from a table with a where condition and put out a number of columns. That's the simplest form you can expect. So let's look at a specific instantiation of that. So this simplest version is straightforward, right? All you do is you scan through your table, meaning that you scan through your files, and check the condition against each record. If the condition is met, you put out the values from the corresponding columns in the select clause. You're done, right? And you use an index whenever that index match the selection condition. If the index does not match the selection condition, you end up doing a linear scan over your heap file. Right? Simple enough. That's essentially what we have talked about so far. What about select distinct? If I add a distinct keyword, things become a little bit trickier, right? Why? Because now you need to worry about removing duplicates. You need to worry about removing duplicates. So how would you do this? Well, one solution is you take the solution we have just mentioned for the simplest version, but you buffer the results you have produced so far and do not push them to output. You buffer them, and at the end of the day, when you have finished scanning the table or finished scanning your index, you have a buffer of all the possible results satisfying the where condition. And then what do? you can either do sorting or hashing on those inputs in the buffer to remove duplicates. You follow me? And we talked about this, I believe, at the beginning of the semester, right? So this becomes then you simply cross this. This is by sorting. Of course, you can also do duplicate elimination by hashing. By hashing, if you do hashing, what happens? It's guaranteed that 2 and 2 will be in the same bucket. And 3 and 3 will be in the same bucket. 5, 6, 7. But of course, this is the ideal case. There's no clear. In practice, you may have clear. So 5 might end up here, 6, 7 might end up here. However, you will never have a case like this where there are many threes here and there are some threes here. This will never happen. Why? Because you're using a deterministic hash function. If the key is the same, they end up in the same bucket. They may have clear, but you will never have cases like that. And this dramatically helps with respect to duplicate elimination, because now you can do what? You can go through each bucket and cross out duplicates, and then finally merge them back to produce the final output. Of course, one thing I didn't mention is you are using hashing, so not necessarily they are sorted. So it may look like this to make your job a little bit harder. You follow me? But that's okay. You can either do a sorting on this data set now to convert this to a sorted order, or you can use yet another hash function to hash them again. And that's called hybrid hashing. And why using another hash function helps? So let's take a look at this example. If I apply yet another hash function, so let's say I do this H1 and use H2 to hash them, what you end up with? These two guys will guarantee still in the same bucket. What about 6 and 7?
Hopefully go to another bucket.
Yeah, hopefully they will end up in another bucket or in another 2 buckets. Of course, you cannot fully eliminate the possibility that they still end up in the same bucket with 3 and 3. But the probability of that is very small. Why? Let's assume the probability for clearance for a single hash function is 1%. So there's 1% probability I will have a clear. Assume H1 and H2 are independent from each other. What's the probability you still see some clear here? 1 is 1% squared. If H1 and H2 are independent from each other. Right? You follow me? Because the probability for you to see a clear here is expressed as what? Is expressed as 2 events, which is the probability that they have a clear in the first level and they have a clear on the second level. That's precisely the multiplication of the 2 probabilities. Why is that? Because if they don't have a clear in the first level, it's impossible for you to have a clear on the second level. Why? Because if there's no clear in the first level, every single bucket will contain just a single distinct value. Then there's no clear to be defined with, to begin with. Because you apply the hash function on a given bucket, not on all the data, on a given bucket in the second level. Okay. So that's how you do select distinct. Okay. Now move on. What about order by? Well, order by, you do this by sorting. And that's the reason why we study external merge sort. Because database files can be super large, larger than the memory you have. And if there is an order by clause, you have to sort them using the external sort algorithm. Okay? So order by, you simply realize this through external sorting we talked about.
So internally, the DBMS would have to, like, because it probably doesn't really in-place sort, it would have to set aside some extra memory and do the sort. And then
What the database system will do is it will check against the memory. They will check the memory size against the output size of this query, right? If the output size is smaller than the memory, they will just use some in-memory sorting algorithm. If the output size is bigger than the memory size they have, than the database buffer, then they will use the external. They will call the external sort algorithm to sort them. Now, what about aggregates? Well, aggregates, if you use aggregates over the projection column, it's fairly straightforward. Depending on what type of aggregates you are computing, but for most aggregates, there are two types of aggregates people typically classify them into. One is called distributive aggregates. And the other is called holistic. So what is the difference? What is the difference? I'll give you some examples, then you see exactly what I mean by distributive and holistic. What are some examples for distributive aggregates? What are some examples for holistic aggregates? Well, case largest is, okay, I will ask you guys about that. So why these are distributive, these are holistic? Can someone argue for me? What is the difference between them? Why, if I give you a classification like this to you, what can you observe about this classification? Guina?
A distributed aggregation can be distributed to many nodes.
Can be distributed to many. Well, we're talking about single node, right? We're not talking about cluster. It's a single node.
But it can be done by a distributed way.
It can be done in a distributed way. More precisely, distributed aggregates can be computed using a divide and conquer strategy.
Yeah.
Whereas holistic aggregates, you cannot. If I want to know the total number of students coming to today's lecture, how do I do? 2, I don't know how many here, then 3, I add up together. If I want to know the median age of all students coming to today's lecture, how do I do? Can I find the median age here, median age here, median age here, then aggregate? No, it doesn't help. You follow me? You have to know the entire data set in order to compute the median. And the same holds for any quantiles. In fact, median is simply the 50% quantile. 50% quantile. Okay? What about, so what's the implication of here to our query evaluation? So, okay, this is fun, but you may wonder why you care. Well, the reason we care is that if it's a distributed aggregate, we can compute this on the fly. So imagine we check record one by one, either through an index or through linear scan of the heap file. We check the matching record one by one, and we project out the aggregate values. If it's a distributed aggregate, I maintain a running variable and compute the aggregates on the fly. So I maintain a single value. Do you follow me? If it's a holistic aggregate, on the other hand, unfortunately, you have to keep the entire set and only compute the value in the very end. This has a huge implication. If you try to, for example, compute the total income, total amount of money people make for people living in Salt Lake City, how do you do that? Well, scan the first one, $10,000. Scan the second one, $20,000. Now the total is $30,000. The trick is, no matter how many people in Salt Lake, let's say 2 million, I don't know, you maintain a single value throughout the computation. If you want to compute the median income of Salt Lake City, well, you have to maintain at the end of the day 2 million values, which is, of course, it's going to be much more expensive. You think about it. What about average, the mean? Well, you can compute that by computing sum and count at the same time. So you maintain 2 running sums instead of a single one. Then you're done. Now, let me ask this question now. What about top K? Or the K's largest element? In other words, using the Salt Lake City example, I want to find the top K person with the highest incomes. Top K highest incomes. How do you do that? Do you need to maintain all 2 million values and then compute this in the end? Harry, no. How do you do that?
No. Sorting the baseline.
Louder. People in the back cannot hear you, right?
Okay. Sorting is a baseline algorithm.
Sorting is the baseline.
So
Well, sorting is the same as maintaining all the values, right?
Yeah,
Because,
sorting all the elements is a baseline algorithm.
sorting all the elements is the same as linear scan, get the values,
Yeah.
and sort them, right? That's you are saying this is the holistic aggregation. Because you do need to know all the values in order to do this. You do need to keep all the values.
Yeah, but we can use a quick sort, the subroutine of quick sort.
No?
Just create a data structure with k values, and if it's bigger than the smallest, put it in the queue, or if it's not, follow that.
Fantastic. Okay? You maintain a heap of size k. While you linear scan the record, either through heap file scan or index, you insert into this size k heap. Initially, the first k elements go into the heap, no problem. The k plus 1th element you encounter, what do? You check this against the tail of your heap, or the head of your heap, depending on how you sort it. If it's smaller than that, what do? Insert this element into the heap and remove either the head or tail, depending on how you sort this, from the heap. If it's bigger than the last element in the heap, what do? Throw it, ignore it. So you linear scan and you maintain only k elements. Yeah?
What happens if you can't store k elements in memory?
What happens if k is larger than memory, right?
Yeah.
That's actually a very good question. So I will talk about this towards the end of the semester when I have time.
Okay.
Essentially, what you are asking is, when we see heap, we by default refer to a main memory heap structure. What you are asking is there an I/O efficient heap or external heap? If you use the main memory heap to do external, to use that as an external heap, it's going to be really expensive. Why? Because each insertion, if it's a main memory heap, suppose data fit in memory, what is the cost for one insertion? What is the cost for one insertion?
Is it log in?
Log in. Charlie says log in. Jian? Who else can help? Jason. June. Huh? The same. Log n.
Well, log of the k, I guess.
I guess that's right. Log k. Why insertion cost is log k? Because your heap size is log k. Essentially a binary tree. To insert this element into the heap, you have to follow the tree to find the right location to put this element into the binary tree. So insertion cost is just log k because you go from the root to the leaf. You follow me? But if you just use the internal heap for external data, meaning the heap is larger than the memory, you log k become what? Log k IOs. Now obviously it's not big, right? What do you expect this to be? You want this to be log what? Log b of k, when your memory size is b. Why? Just like binary tree is log n, bpower tree is what? Log b of n. So we want to have the same kind of cost comparison here. I'm not going to argue to you how to do this. It's actually not that trivial, but I'm going to show you, since he asked this question, how do you make a queue? You all know a queue structure, right? How do you make a queue I/O efficient? Since we come to this, let's talk about it. This could be your final exam test, right? How do you make a queue I/O efficient? If you use a queue as it is, like an internal memory queue to external data, what is your I/O cost for insertion and deletion?
So for insertion, you like shift everything.
A queue is very simple, right? Insert just append, delete is just remove the head. So let me ask this question. Not even external, internal memory queue. What is the cost for insertion and deletion in big O notation? Jonathan, what is the cost for
Inserting and deleting out of the queue. Isn't it just constant?
Okay, O1, right? Constant. Append to the end, remove to the end, or remove from the head. You follow me? If you use this internal memory queue for external data, what happens? The insertion cost and deletion cost become constant I/O, right? 1 I/O. Why? Because this is the queue. But remember, now the picture is slightly different. This is the queue, but they reside in different pages. You follow me? Let me finish. And when you insert an element, this is the head, and this is the tail. When you insert an element, what do you do? Pin this page, buffer. There are 3 items here, add it to it, and then what? Write it back. So how many IOs? 2. In big O is what? Constant. Deletion is the same. You pin this, remove 1, and write it back. You follow me? Is that the best you can do? Can you do better?
Wouldn't an external queue be essentially what we're doing for the external sort?
No.
Because we're taking something from this.
Sorting, you're not doing any insertion and deletion, right? You're playing with some existing set of data. Here, you're adding new item and removing items. So
I think we just like, instead of inserting and deleting one at a time, we have a chunk buffer main memory. When it fills up, then we add it to the queue.
Do all of you hear that? That's the idea, right? In fact, that's precisely the idea. What you do is you allocate 1 page in the buffer. You want to do insertion, right? Fine. I just keep inserting to it. When this is filled up, what I do? Write it to disk. So what's the cost for insertion? Let's say your page size is B, okay? Page size is B, but meaning every page can hold B items. What is the cost of this insertion? You do 1 I/O for how many items? So the amortized cost is 1 over B I/Os instead of 1 IO. That's a huge improvement. The typical value of B is what? Is hundreds or even thousands. You follow me? So that's a huge, huge difference. What about deletion?
You just end the
Well, you just buffer the head page in the buffer all the time. Keep deleting from it. When it becomes empty, what do you do? Then you tell the queue structure this is empty, remove it. You may wonder, well, that's not right. The content of the head page on disk and the content of head page on buffer is different. But that's, if you understand buffer, how buffer works, that's no problem, because any request to the head of the queue will be served by the copy of the head page in the buffer, not by the copy of this page on disk. So the deletion cost become what? Amortized cost is 1 over B again. So using a simple structure as queue, I convinced you the difference between internal and external memories structures. Okay? You can make the same argument now on your own to stack, to graphs, to all the different structure you use in your code. Linked list, how do you make an external memory IO efficient linked list? How do you make an IO efficient X, IO efficient Y, IO efficient B? Some of them are trivial, like Q is trivial, but some of them are not. You follow me? So, if you think you know programming, think twice, right? If you write this queue and use it on Google data, and versus the queue I have implemented, I'm gonna beat you 1,000 times, easily. Right? I do the analysis. You pay 1 IO per insertion, I pay 1 over B IOs per insertion. No match at all. So if I'm Google, I can ask you an interview question as, can you implement a queue for me? You may think, what are you talking about, implement a queue? Are you nuts? Well, they may say, okay, implement a queue for 100 items. You got your queue structure. You say, okay, now it's 1 billion items, 10 billion items. That interview question now become interesting, right? I guess many of you, if you don't know IO efficient stuff, you will not be able to answer that question actually. If you write the queue as it is, you will fail the interview, I think. I mean, if I were the interviewer, if you write your queue like that, I will fail you for sure. Okay. All right, so that's order by, and what about group by? That's okay. We talked about top case. What about if I just want to find the case element, case largest element? Of course, the top case solution is a baseline for case largest element. I can maintain a size k heap. And then at the end of the day, I just output the case element from the heap. I'm done. Can you do better? I leave that as a question for you to think about. Okay, let me move on.
Isn't there an online algorithm or something?
That's my question. Yes. And goodbye. Okay. What about goodbye? Typically, goodbye is followed by some kind of aggregation. You partition the record into different groups, and you compute an aggregate per group. And how do you do that? Well, and sometimes you may even have a having condition on the group, right? So let's look at how we do this goodbye. I will talk about this overview first, then we talk about how we do the goodbye and having aggregates. So in a relational database engine, what happens is a SQL query will be translated into a graph like this, a pipeline graph like this, where each oval shape here or circle shape here represent an operator, and each arrow represents the flow of your data, So let's look at this example to understand what's going on here. So what this operator says is, I'm going to do a heap scan. Of course, at the bottom of this graph is your base relation, is your table, which is students. By the way, all right, I think one thing I want to emphasize is from here onwards, right, we have passed the most difficult programming assignment. Okay, But the most difficult part of the lecture is yet to come. Okay? All the things we discussed so far will be trivial compared to what I'm going to discuss in the next few lectures. Right? Especially when we come to pure optimization and transactions. Okay? So I do ask all of you to pay attention in lecture. And those of you who are not here today, maybe some of you are watching the streaming YouTube video, I encourage all of you to come to the lectures. Right? Because the midterm average was, what, 76? And if we keep everything, keep it like, call that status quo, we keep everything the same, with the content I'm going to cover for the second part of the course, I expect the final average will be 66. Unless you study harder than what you have done for the midterm. Okay? The second part of the course is much harder than what we have talked about in the first part of the course. So heap scan, student come here. This represents data flow. That means you, from the student record, you produce name and GPA values. You scan the records and you put out these two fields from each record. And these two will go into this operator called sort. And then after you sort, the output of this is still only two fields, which is name and GPA. You follow me? Yes? But the difference between here and here is now they are sorted. And then you apply the distinct operator to produce the final list of name and GPA pairs. So that's how you understand this query graph. And this oval shape is implemented through an iterator interface. Meaning every operator in a database engine actually implements this interface. So how many of you know this concept called interface from object-oriented programming? You all know, right? So this is not a C++ specific concept. I believe in Java you also have this thing called interface. Interface in Java is essentially an abstract class. Okay, that's what an interface is. Okay, so all these operators implement this iterator interface, and this interface is defined as follows. It has an initialization method, it has a close method, then it has a next method which returns you a tuple, a record. And then it also has an array of iterator as its input. Okay, if we look at the example I just showed you, you immediately understand why this iterator is defined this way. Why? Because each iterator will have an input, which can be viewed as another iterator. And each iterator fetch its data from the output of the preceding iterator. That's essentially the purpose of the next operator. You follow me? Going back to the example from the last slide, the sort iterator, its input is an array of iterator, in this case of size 1, which is a heap scan iterator. And the sort will call next repeatedly to fetch the record from heap scan. And when the next method is called, the heap scan simply move on to scanning the next record and push that to the sort operator. You follow me? And what about initialization and close? Well, those are designed for setting up the initialization state and cleaning up memory and things like that by the end of the execution of the current iterator. Okay? So you put that number 5 is to implement this iterator interface for one operator, for a particular operator, which we will discuss later on. Of course, obviously not a single table operator, because that's too trivial. It will be a join operator over multiple tables. To give you an example of sort, essentially, actually, you will do both. You do implement the single table iterator and the multi-table iterator. You put that for the sorting product is actually a single table iterator, which is to implement the sort operator over a single table, the X number sort. Okay? So this will be a realization of the iterator interface for the sort operator. What do you have? You have this, and you have some state variables, the number of rounds and things like that. You have initialization and close. And how this works? Well, let's look at this together. The initialization phase will be your phase number 1 in our axiomer sort discussion. Initialization will be your phase 1, which means you generate sorted rounds on disk. Here you can use either the baseline algorithm, which is load B pages, sort them down to the disk, or you can use what? The improved tournament sort, which on average produce a run of 2 B pages. But for simplicity, for you implementation in Product 4, you can just use the baseline algorithm, sort B pages down to disk. You follow me? So that's what you do with initialization. And that's why you have this array of disk block called rounds. So it's an array of rounds, essentially. It's an array of rounds. And if you use the baseline algorithm, what's the size of this array? Well, it's n over b, the ceiling of that. That's the size of this array. Follow me? What about the number of rounds? Well, the number of rounds is calculated at the end of the initialization phase, depending on the number of pages you have, which is n, and which algorithm you use. Whether it's B or 2B, right? If you're using the baseline or you're using the tournament sort. So that's the initialization. What about the next RLE? Well, this array, you can think about this as those cursors you maintain during the merging phase. The B-1 cursors you maintain during the merging phase. 1 cursor per each round you are merging. Do you follow me? So the size of this array will be B-1. If you have B pages in the memory, the size of this array will be exactly B-1. Why is it called next RD? Well, because essentially the cursors point to a record. So these cursors are represented by the RAD value of the next record from the corresponding round during your merging process. What about next? What about the method next? Well, next will produce the next tuple in the merging process. In other words, whenever somebody calls next, what do you do? Well, you check all the records pointed by the next RADs in the next RAD array and return the record with the smallest value when somebody calls next.
Would that necessarily give it a sorted order?
It gives you the sorted order in the current round. It doesn't give you the sorted order in the entire.
So there would be another layer on top.
Is another layer on top to make sure that you finish the merging phase before the next iterator in the pipeline can actually fetch the record from you. Make sense?
So, and there most likely, would there have to be some kind of buffering below this layer from the heap file to the, because you wouldn't be,
So I guess when I say pipeline, it doesn't mean all the operators will be able to process tuples in a streaming fashion. Some of them are blocking, some of them are not. So the pipeline might be confusing in that sense, because by saying pipeline, automatically, most times it implies a streaming process. But in our case, depending on the operator, some are streaming, some are not. Like heap file scan is a streaming pipeline, but sort is not. Okay. And close, you deallocate the round and next RD arrays. And basically, in your product 4, you will implement this method. Now, that being said, now let's look at the group by and aggregation I talked about, right? With this being discussed, I can express the computation for group by aggregation using this pipeline now, using this pipeline graph. One way to implement this is to do what? Sort, then aggregate. Why sort and aggregate help you to do group by? Well, if you sort by grouping attributes, obviously that helps. Suppose you have a student record, right? This is age value. And why sort helps? Of course, sort by age. This become, you agree? And that's essentially is you grouping. And then you can do the aggregate. So this is sort operator. Now what can you do? You can do the aggregate operator on the fly. Why you can do this on the fly? Because suppose you are doing sum. That will output 10 and output 14.8 respectively. And you can do this. This is the streaming pipeline. This is not. You can do this in a streaming fashion, right? Because you maintain one running sum for the value you have seen so far. Whenever the value is different from the last value you have seen, you output the current running sum, you will set to 0 and continue. Okay. An alternative to sort and aggregate is to use what? Which is the thing I discussed at the beginning of the class, which is hash. Of course, you hash on the aggregate, on the age operator, on the age attribute, sorry. So you can change this pipeline graph to hash, then aggregate. You follow me? And let's take a closer look at hashing. Hashing suffers this potential problem of cleaning, like I discussed. And the way you address cleaning is to do what? To hash the cleaning bucket yet again, right? So this is what we call the famous two-phase hashing algorithm. There are two phases. I'm going to show right here. The first phase is called partition. The second phase is called rehash. Okay, let's go through this together. And I will have two hash functions. One is a partition hash function HP. One is a rehash function HR. So the partition phase is very simple. I use one input buffer and B minus one output buffers. So my total size is B memory pages. So I load in a page at a time from disk, then I apply the partition hash function HP. And the output of the partition hash function will be one of the B minus one buckets. It will be one of the B minus one buckets. Which means an element from the input buffer will end up in one of the B minus one buckets. You follow me? Yes or no? And whenever an output buffer is filled, remember, in this case, each output buffer is simply a single page. So whenever it has a page of data, what happens? You push that page of data to the disk. But on disk, you maintain B minus one partitions. You maintain B minus one partitions, like I show in the graph. At the end of the day, when you have scanned through all the pages, they become pages on this B minus one partition on the output. So the partition phase, effectively what it does is to take n pages and group them into B minus one partition on disk. Okay, what about the rehash phase? Here it is a little bit tricky, but not too complicated. Okay. Let me finish discussing this, then we adjourn for today's class. The rehash phase does the following. It handles one partition at a time. It processes one partition at a time. So start with the first partition. What I do? I load the partition into the memory. Then I hash them again using a rehash function HR. But this time, one important assumption is I assume that this partition fits entirely in my memory. Assuming my partition hash function is a good balanced partition hash function, what this condition says? This condition says You have n pages to begin with. You push them into b-1 partitions. So roughly the size of each partition is what? Assuming a truly balanced hash function. The size of each partition is roughly this. The size of each partition. Right? Now, assuming each partition fits in memory, what does it mean? That means this is less equal than b. Because my memory size is b. Which implies what? Okay, so that's the condition. When your memory is greater or equal than square root of n, and if you're using a good partition hash function, you can safely claim that each partition will fit in my memory. Now, why this is important? Because if that's the case, your rehash phase is very easy, right? You process one partition at a time. Because this partition fits entirely in memory, what do? Load all them into the memory and build an in-memory hash table. And then remove duplicates from each bucket from this in-memory hash table. The probability that you still have many clearance in the rehash phase is very low by the argument I gave you earlier. If the rehash and partition hash function are independent from each other. Do you follow me? What is the total I/O cost of this algorithm? Assuming this is true. Assuming this is true, what is my I/O cost? Well, in partition phase, I load n pages in. How many pages I write to the disk? I write n pages to the disk. It's just that they go to different partitions, but in total I write n pages. So that's 2n. What about the rehash phase? Because each partition fits in memory, I load each partition once into the memory. I never need to do any additional I/O. I load n pages in total. By the end of the day, by the end of finishing every partition. So my total cost is 3n. Of course, with this assumption. What happens if this assumption does not hold? What will happen?
You'll have to flush some of the pages to this rehash phase.
When this doesn't hold, like Charlie said, essentially what that means is some partition, not all your partitions, but there will be some partitions that will not fit in B pages. So your rehash phase cannot be carried out because you cannot build an in-memory hash table for them because they're bigger than in-memory. What do? Well, take these partitions, assuming there is a partition that's bigger than B. Take this partition and treat it as your input and apply this two-phase again on this partition recursively until every single partition fits in memory. But you don't have to do this for all the partitions. Only do this recursive step for the partitions who do not fit in your memory. And with that, I stop right here. I see you on Tuesday again. Okay? And there's the analysis here.
So when your next phase, once you've done the rehash, then the next phase could call the iterator and start.
Well, this hashing and aggregate thing is not a 100% streaming pipeline operator. It is a streaming operator in the sense that whenever you have done this in-memory hash table for a given partition, once you know you can build this in-memory hash table for a given partition, at that point it becomes a streaming operator.
Right. Yeah.
But before that, it is not streaming. It's blocking.
So you still have to like sort in each bucket, maybe.
That's optional. If you want to improve the CPU cost, yes, you can do a sorting. But even if you do linear scan, it's because it's already in memory. Hopefully, it's not too bad.